for the next 10 minutes, I just really want you to do a little thought experiment and think about everything that you're working on in aquaculture technology, the organisms that you work on. Imagine like how they would operate in a gravity-free environment and how it might impact them. So, bear with me and I'll explain to you why it's important. But to get into that, a brief history of spaceflight. So I'm not going to go through all this, but we've been doing space research since 1947 and before that. Basically, space, the International Space Station, whenever it came on board in 2011 was whenever it was completed, and a lot of researchers utilized, it was designed specifically to do research in space and to allow that to happen. So we've done human research, agriculture research, all kinds of things. Unfortunately, aquaculture research has gotten the short stick of this treatment for a multitude of reasons. So here I am. I've been in the space industry for 6 years. I've launched over 100 different experiments to the ISS. I am not an aquaculture person. I am very much a space person. But we found this niche market and a niche kind of research potential that we wanted to offer to people. So I really want to develop this aquarium for space to allow researchers to do research. And just for fun, here's a few things. So this is a plant research or a plant growth chamber. These are satellites. We baked cookies in space. So this is an oven made by Hilton. This is a wine bottle that was sold for like $1 million because it went to the space station. I'm helping some kids in Saudi Arabia do space experiments here and all kinds of things. So an aquaculture research platform for space. Basically, there has been some research in space on aquaculture. However, it's been super limited based on essentially the facilities that have been available. So originally, JAXA, the Japanese Space Agency, launched this aquatic habitat, the AQH they called it. It had 1.5 liters of available usable volume, and it did all kinds of things. It was essentially a 1 liter rat. And so what they studied in there was these Medaka fish, which are extremely small. They've studied brine shrimp and they've studied bobtail squid. Some other platforms that they've done is, this is another company's platform called the AdSet. Again, super small, very limited, I think 1/2 liter in that tank. This is a proposed experiment for the ISS called Scampi, where they're studying shrimp. And then this one actually was just flown in 2024 on the Chinese space station, which is called Tiangong. But again, it's very, this is again probably a 2 liter tank. And so while there has been some research performed, it's been at such a small scale that I think we've been very limited in what we can learn from what we're doing. And that's why I wanted to take it to the next level, really, and build a much larger tank for the ISS. So this tank, it will be 30 liters. It has partitions in it, so those 30 liters could be divided into up to 9 separate independent tanks. We could also kind of connect all that. It'll be a fully closed and autonomous system. And we're capturing imagery, all kinds of sensors, or all kinds of data. And the goal here would really be to study whatever you want: oysters, fish, algae, symbiotic relationship between the two. For example, we've spoken a little bit with the Horn Point Lab a while ago about doing like an oyster larvae, kind of how it navigates the water column experiment in microgravity. So we're kind of carrying that forward. And I think a question that you still might be asking yourself is, why would we do this? Which I think is a very fair question. And I think a good analogy of this is plant research that we've done in space up to this point. So as long as we've been launching rockets, back in 1947, we've had seeds and other plants that we've launched to the ISS, or launched to the low Earth orbit and studied them. So right now there's 2 plant growth facilities on the space station. This is the veggie platform. It's kind of like an open, it's just like if you had pots in your house and you were growing plants. And then this is the APH, which is the advanced plant habitat. And this one's a completely closed system, studying all kinds of stuff. They've grown tomatoes, peppers, arugula is like a model organism, so they study arugula a lot. And from this, we've learned how plants' roots grow, how their phototropism affects their growth, how stress impacts their genetic expression in space, and their physiology and their biology, and that has really led to improved crop yields and impacts on Earth as well that we've utilized. Not to mention that in space, in the development of these systems, we've created new technologies to help these plants grow. So advancements in hydroponics, in LED lighting, and understanding that we've done that so that we could grow them in space, and it's led to technology advancements here on Earth as well. So essentially, I want to take what other people have done growing plants in space and apply that to aquaculture and get the same benefits that we've done there. So jumping into the benefits for Earth, the two things that I think we really want to hit on is food security and kind of globally climate change in general and the impacts of that. And so on the food security side, the real thought process is that we could learn something about the genetic makeup or how plant or aquaculture is affected in microgravity that would benefit their impact here on Earth. So maybe we learned that oysters produce their shells a lot faster, or their yield increases in microgravity, and we can take that knowledge and apply that to our Earth aquaculture systems. Beyond that, like I said, with these other advanced technologies, NOAA already does all kinds of oceanic monitoring in space. There's already kind of these parallels, but they have not been applied to aquaculture specifically yet. And that's pretty much the primary goals that I want to study for Earth. And then there's also impacts for space as well. So for space flight, a major problem right now is, we can go to low Earth orbit, which is about 100,000, well, the line between Earth and space is 100,000 kilometers. So beyond that is low Earth orbit, where the ISS orbits the station. And right now, we just launched food for crew members to eat. We launch about 4,000 kilograms of food a year to keep them alive. And every one of those kilograms costs about $50,000 to launch to space. So every year we probably spend $200 million just keeping crew members fed on the International Space Station. That's okay for low Earth orbit. It's a ton of money, but that's okay. But if we ever go to the moon and Mars, which are huge goals for the ISS program and for NASA and for other space agencies, right now it costs $1 million to go to the moon, and to go to Mars is just completely out of the question at this point. So everybody in the space industry is really considering what's called bioregenerative life support systems. So essentially building a terrarium that operates in space. So most people are focused on plants for that, and plants recycle oxygen. They have a ton of nutrients, but in terms of like macronutrients, they're very limited. So I'm also proposing to this regard that we could use aquaculture as a part of this, as a component of this overall system. And that's why I want to focus on basically building this box in the ISS in the near term, up until 2030, and then we'll transition into focusing on food production capabilities in space. All the while benefiting life on Earth from the research that we acquired through that. So I think I'm probably way perfect. Okay. So this is from The Martian. I don't know if you've seen the movie. It's a great movie. I just read Andy Weir's other book, Project Hail Mary. Highly recommend. But I just threw some oysters down instead of the potatoes he grew. So in summary, though, I think there's a unique opportunity here where innovation from aquaculture and what NASA wants to accomplish and what the space industry wants to accomplish in the next 10 years has an interesting intersection point. And I think so, why do we want to do this? And it's because food in space is a necessity, food on Earth is a necessity, and there's applications for both that we can glean from this. I think why now? Like I said, it's a very interesting point for both. Why our product? Because there's currently no other capabilities of doing this. So we're currently applying for SBIRs. We have a couple other funding methods coming in.